Okay, so today we'll continue talking about the Bayes classifier, and then we'll bring in the naive Bayes classifier. So I think this is where we left off, somewhere around here. And so this is just a bit of review here. With the Bayes classifier, we are going to we're going to apply Bayes' rule. Okay, which says the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. And we're going to apply that for a classification problem where what we want to know is the probability that some observation belongs to a certain class given the values in its x vector. Okay, and the way we're going to find that, this we call the posterior probability. Okay, probability an observation belongs to class C, given its x values. The way we're going to find that is we're going to switch basically this side and this side, which gives us the likelihood, and we're going to multiply that by the prior, and we're going to divide that by the marginal probability. Okay, so the likelihood is the probability of x nu given basically that the label is class C. It's the probability of observing the values in the x vector if we assume that the observation belongs to class C. Okay, and then we multiply that by the prior, which is just before you even look at any observations, what's the probability that this new observation belongs to class C, and that's often equal to the proportion of observations that belong to that class in the training data. And then we divide that by the marginal probability, okay? And we can find this by summing the numerator. We can take the numerator and sum across all possible values of C. All right, so let's review our simulated data, okay? And so what we've done is we've generated data using the multivariate normal package, okay? And for two of these things, the covariance matrices are diagonal, indicating that x1 and x2 are independent, okay? One set is centered at 2, 3, another set's centered at 0, 0, and another set of data is centered at 2, negative 2. This set of data has a covariance matrix that exhibits high covariance. Okay, and so when we plot it, this is what our data looks like. Okay, we've generated data centered at 2, 2, 3, 0, 0, and 2, negative 2. And I've drawn some contour lines kind of indicating the multivariate normal probability density. Okay, and they're represented by these ellipses. Okay, and again, this is kind of most of the data will come in the center circle, and as you go farther out, it becomes less and less likely from the center. Okay, so the estimates of the way we're going to do this is we're going to estimate the parameters, okay, because we want to figure out this likelihood. And so to estimate the parameters, we are going to just take the means, column means of each class. So I've got 30 observations that are labeled A, and I'm going to take the column means, and that's going to form my X bar. Okay, and then I'm going to take the variance of my observations labeled A, and we're going to make that the estimates of the variance. Okay, and we do the same thing for class B and class C to get X bar B and X bar C and variance of B and variance of C, and these are all estimated means and estimated sample variances. Okay, and so if I estimate my means and variances accordingly, this would be kind of the estimated contour lines, right? So this is the estimated normal, multivariate normal distribution that's been overlaid on top of our data, okay? And we can see that this is a little bit different from the generating data, because the generating data is centered here, and this one's its center is a little bit off from that. And also the generating data for the blue and the red dots, the x1 and x2 variables are independent. And so, so that's most noticeable in that the ellipses, the major and minor axes, are not parallel, not perfectly parallel to the x1 and x2 axes. And because if they are independent, then the major and minor axes of the ellipses would be parallel to the major and minor axes here, and they're not exactly parallel. They're kind of close for these two, okay, but they're not quite so, right? You know, for the green dot data, the generating distribution was not parallel, and our estimated density fit is not parallel either. Okay. So so anyway, this is what we've estimated. We don't get to know the known contours. We don't get to know how the data were generated in the first place. We only have the estimated contours. But so we're going to use the estimated contours to figure out, calculate the probability of a new observation belonging to a particular class. Okay, so this is my test case. This is going to be my test case. I'm going to put it at 0, 0, right? And so just looking at this, if you saw a dot here, I think we would all agree that this dot belongs to the blue class, right? It looks very clearly that it belongs to the blue class. So, but if I told you it didn't belong to the blue class, you know, then the next most likely would probably be red. Okay, its contour lines are approaching this dot, and then the least likely would be the green, because it's quite far away from these contour lines, indicating that it would be, you know, an extreme value here. But the most likely would be the blue class, right, for this test case right here. Okay, so how are we going to find the class probabilities? Okay, well, we are going to use our Bayes classifier. Okay, the Bayes classifier, again, is the posterior probability, which is equal to the likelihood times the prior divided by the marginal. Okay, so what we want to find this, and we're going to find this by first calculating the likelihood. Okay, the likelihood in this case is the probability of getting x new given a particular class C. Okay, we have three classes. We have red, blue, and green. And we're going to say, well, what is the probability of getting the value 0, 0? What's the probability of getting the value 0, 0 if we assumed the if this observation came from the red class? Okay, and then we ask, what's the probability of getting the value 0, 0 if it came from the blue class? And then what's the probability of getting 0, 0 if it came from the green class? So, and we're going to calculate this using the multivariate normal density. That's the likelihood. The prior is going to be the probability that our test case belongs to a particular class, okay, before we know anything else about it, okay? And so for that, we're going to use the proportion of observations that belong to class C, okay? And so we're going to say, well, what's the proportion that are red, what's the proportion that are blue, and what's the proportion that are green? And we're going to use those as our prior probabilities, okay? And then the marginal is we just calculate the numerators across all possible classes, and then we're going to add those up together, and that's going to be the marginal probability. Okay, so the multivariate normal PDF has this this equation, okay, and so so I went ahead and I calculated the multivariate normal PDF. I did 1 divided by 2 pi raised to the d over 2. We are two-dimensional, so we have 2 over 2. So I guess 2 pi to the 1 times, this is the determinant of our variance matrix. And for class A, our estimate of the variance matrix is var underscore A. We just calculated that by taking the sample variance of our data points. The determinant raised to the 1/2 power. Okay, and that's this first constant up here. And then we multiply that by exp of negative 1/2 times, and our new observation is 0, 0, x new minus x bar transpose times the inverse of the variance matrix, which is solve var A, times x minus var A. Okay, and when you calculate this, you're going to get a scalar value, and that scalar value is 0.000879539. Okay, so so we can use the multivariate normal PDF and plug it in and get this. Okay, fortunately for us, there is a function in R that does the exact same calculations, and it's a lot easier to use. You use it much like the d norm function, okay, except we call it dmv norm for multivariate normal, right? And for this, we give it the vector of our test case. In this case, x new is 0, 0. We're going to say, what's the density for x new if the mean is x bar A and the variance or sigma matrix is variance of A. Okay, and when I do this, when I call dmv norm here, I get the exact same value that I have on the previous slide, 0.008795399. Okay, so we can see that using the equation manually by doing all of these matrix operations here and figuring out the determinant and all of that results in the same value that the DMV norm does. Okay, so so that's good, and so to kind of keep my life easy, I'm going to just go ahead and use DMV norm for all of the observations here. Is that okay? So I calculate the likelihood. All right, now let's just look at these numbers. So we say, well, what's the likelihood of getting 0, 0 if it came from the red class? Okay, so that was 0.0008. So about a little under 1 in 1,000. Okay, that this that you would get a point like this if it's generated from the red distribution. Okay, and here, what's the likelihood of getting this if it's coming from the blue distribution? That likelihood is a lot higher, around 16%. Okay, and then what's the likelihood of getting the observation if it came from class C, which was the green distribution? And that's the smallest. That's on the order of 10 to the minus 5. Okay, so our likelihood numbers match our intuitive sense. Okay, all right, so so that's the likelihood, and now we want the prior probability. Okay, the prior probability is the probability that our test case belongs to a particular class C before we know anything else about it. And so for this, we're going to use the proportion of observations that belong to class C in the observed data. All right, and in our simulated data, all three classes, the red, the blue, and the green, they all have the same proportion of observations. They all have there's a total of 90 observations total, and each class has 30 observations. So all three classes are going to have the same prior probability of 1/3. Okay, so because all three of them, the prior of A, B, and C, are all equal to 1/3, it's technically not necessary to include them in the calculations because they're all going to cancel out with each other at the end. But just kind of for consistency, to kind of stay consistent with the Bayes rule formula, I'm going to go ahead and include them here. Okay. All right. Maybe I'll just pause here for a moment. Is everyone okay with where I'm getting these likelihood numbers? Okay, I'm using the multivariate normal and then the to define my multivariate normal, these are estimated X bar and estimated variance matrices coming from the data. Okay, if this all makes sense and if this feels good to you, go ahead and give me a green check mark so I know you guys are doing okay. And if you got any questions, enter them in the chat or raise your hand. Okay, I guess I can give you the first answer for our quiz question. First answer is D as in dog. D as in dog is the first quiz answer for today. D as in dog. All right. Okay, so that's the likelihood, and here's our prior. Okay, and then so the marginal probability, the value that goes in the denominator, is going to be equal to the sum of the numerator, and we find the numerator by doing the likelihood times the prior. Okay, so we're going to do likelihood times prior, and we're going to do that for all the classes. Okay, so we do the marginal is equal to the sum of the likelihood times the prior for A, likelihood of prior times the prior for B, and the likelihood times the prior for C. Okay, so that gives me the marginal probability. Okay. All right, and so remember, for Bayes' rule, the posterior probability that we want is going to be the likelihood times the prior divided by the marginal. Okay, likelihood times the prior divided by the marginal. Okay, and so I've calculated all of these values. And so if I do likelihood times prior divided by marginal, this is going to be the probability that it belongs to A. And we have 0.005, so about 1/2 of 1%. Okay. The likelihood that it belongs to class B, okay, is around 99.5%, 0.9946. Okay. And then the likelihood that it belongs to class C, okay, so I do likelihood times prior divided by the marginal. This is around 10 to the minus 5, okay, or 10 to the minus 4, because it's 0.99.87. All right, so around 1 in 10,000, around 99.5%, and about 1/2 of 1%. Okay, so as we expected, the probability that 0 belongs to class B, which is the blue dots, is going to be the highest. Okay. All right. And that's how we go about calculating the probabilities that it belongs to each class using the Bayes classifier. Okay, let's just try a couple other examples. So here we can do another test case. This one is at 6.2. Okay, so looking at this, looking at our chart, where would you say this dot belongs? This test case right here. Red, blue, green. Okay. Yeah, so it's kind of on the outskirts, but yes, as far as it goes, it seems like red would be the most likely. Okay, and then the second most likely would be green, and then blue would seem the least likely. Okay, out of these. Okay, here are the answers. Okay, so I just put this all on one slide. We have our x new is the observation 6,2. All right, x bar and variance of A and x bar and variance B and x bar and variance of C. These have already been calculated on a previous chunk of code. And again, these are just estimated using, these are not the actual distributions, but these are just estimated using the observed data, right? So using the estimated means and variances from our data, we calculate the likelihoods using our multivariate normal density. That gives us the likelihood of A, B, and C. We calculate the priors, which is just 1/3 for everybody. And then I calculate the marginal, okay, which is going to be the sum of the likelihood times the prior. Okay, and I think here it becomes clear that when the priors are all equal, I could easily factor out the 1/3 and they would all cancel each other out, but it's not necessary. Okay, so we can leave that in there. And then so the probability that 6-2 belongs to class A, if I do the likelihood times the prior divided by the marginal, I get something around 80%. Okay, 79.5, 79.48%. Okay, the likelihood that it belongs to class B is on the order of 10 to the negative 9. Okay, so very highly unlikely. And then the likelihood or the probability that it belongs to class C, the posterior probability, okay, I do likelihood times prior divided by marginal, that's around 20%, 20.5%. So we see class A has the highest probability, as you guys, or as my two students who participated noticed, and then class C would be the next most likely. Okay, what if I pick another point and I just move this one a little bit closer this way? Okay. All right, so if I move the point over to here, now what? Now which class do you think is most likely? Okay, this one's a little bit harder. Okay, should it be the green or the red? It's a little bit tougher to tell now. Okay, and so so this one, our test case is at 5,1. Okay, 5,1, which is right here. Again, I do my calculations, and we get something closer to 50-50, but not totally 50-50. Okay, and this is found using DMV norm. Okay, using the multivariate density, we get the likelihood of A, B, and C. Okay, using each thing's respective estimated variances and mean values. Okay, and so here, this is the prior probabilities. We get the marginals doing likelihood times prior, the sum of the numerators. Okay, and then when we run these calculations, we get something around 39% for A, 61% for class C, and basically 1 in a million for class B. Okay, and so it just favors class C a little bit more than class A here. Okay, and then and here's one where I kind of put it in the middle of the red, blue, and green dots. And if we and I think this one is at 2.53, 0.37, and it's really sensitive. Like if you just move it over 1/100th of a value, or a 1/100th of a value another way, these probabilities shift, pretty quite a bit. So but here we get something close to around 30, 35, 36% for each one. So I got around 31% for A, 36% for B, and 33.5% for C. Okay, so we've got these different probabilities here. Class B is technically has the highest probability of the groups, but all three classes have similar values here. Okay. So that is that's the Bayes classifier. Okay, and again, we do this by doing likelihood times the prior divided by the marginal, and the likelihood is calculated using some kind of density value, right? So in today's lecture, we looked at the multivariate Gaussian, the multivariate normal, but then on Monday's lecture, we saw it applied to the Bernoulli, or the binomial distribution for the likelihood. Okay, so you just have to kind of think, you have to create the distribution, or use the probability distribution that's appropriate to calculate your likelihood. Okay, the priors is going to be, we often use the proportion of observations that belong to a particular class C. And in today's example, all three classes had the same proportion. But in Monday's example, it was a little bit different. We said, half of the bags. Remember, we were doing the example where we had a pouch, and inside the pouch there were marbles, and the pouches came from different factories. And in Monday's example, we said half of the pouches came from factory A, so therefore our prior probability was, 1/2 for A. And then the marginal is the probability of observing your values regardless of the class label, but to just calculate that, we're going to calculate the numerator, which is the likelihood times the prior, and we just calculate it for all possible classes, and then we add that up, and that gives us our marginal probability. Okay, so so that covers the Bayes classifier, and so what I want to do is I want to introduce the naive Bayes classifier. Okay, so so if we look at the multivariate normal distribution, this is what we have, and we said that if sigma, if this matrix is diagonal, okay, meaning the off-diagonal elements are 0, then this thing can be factored into the product of univariate normal PDFs and univariate Gaussian PDFs. Okay, and so so this is what the naive assumption is. So when it's the naive Bayes classifier, it's the Bayes classifier, but we make a naive assumption. Okay, and the naive assumption is that the x variables are independent of each other. This is often not the case. Usually, we would acknowledge that there is some correlation or covariance between our x variables. But here, to kind of make our lives easier, we intentionally make this bad assumption that the x variables are all independent of each other. Okay? And the reason we would do that is we end up getting something a little bit more useful. Okay? So for one, okay, well, in the case of the multivariate normal, it's not that big of a deal. We understand the multivariate normal quite well, and we can calculate the probabilities. But depending on the situation, we might not know how the joint distribution looks with all of these different variables going on. Okay, and it might be easier to estimate the joint distribution as a product of independent distributions, okay, rather than trying to figure out the covariance and correlation between x variables. Okay, the other part that's important is that if you have a lot of x variables, then the covariance matrix gets bigger and bigger and bigger, right? It grows on the order of d squared. So if you have two variables and they're independent, there's only two variances that you need to calculate. You need to calculate variance of variable 1, variance of variable 2. Okay, but if you say they're dependent, then you have a matrix and there's 3 unique values to calculate. Okay, you've got the variance of 1, the variance of x2, and then the covariance of x1 and x2. Okay, but if you go up to 3 variables, now you have 6 values that you need to calculate. Okay, you got variance of 1, variance of x2, variance of x3. Then you have the covariance of x1 and x2, covariance of x1 and x3, and the covariance of x2 and x3. Okay, but then if you go up to, say, if you have 10 x variables, then you have 55 variance covariance terms to calculate, right? You've got the variance of x1 through x10 individually, and then you have the covariance between x1 through x10, x1 and x2, x1 and x3, all the way through x1 and x10, and you have every other, you have to calculate the variances of, x7 and x9, and x9 and x10. You're going to have 55 values to calculate. And depending on how many observations you have, your estimates of the variances could be wildly off, right? If you're only using maybe like 3 observations to get a variance estimate, your covariance estimates could be wildly off. And so perhaps it's easier and more reliable just to assume that the covariances are 0, or that if there is a difference, it's not going to be a huge difference. So, so what this does is that when we do our likelihood calculations in the when we do the likelihood calculations for the naive Bayes classifier, instead of using the multivariate normal density, we just take a product of univariate normal densities. Okay, so in our example, we have a two-dimensional data. So I'm going to have the normal density for x1 multiplied by the normal density of x2. If you have a high dimensional thing, you're just going to multiply, like if you have multivariate normal in 5 dimensions, you would take 5 univariate normal densities and you would multiply all 5 of them together. All right, so I'm going to use the exact same simulated data as before. Okay, so this is the data that, these are the distributions that simulated our data. Okay, so these ones are independent. So the assumption of x1 and x2 being independent is not going to be a problem for the red and the blue class. Okay, but it will be an issue for the green class because the green class exhibits high covariance. Okay, and so so this is how we estimate the parameters now. So the parameters, there's going to be a lot more parameters to estimate, but they're actually a lot easier to estimate. So here, I'm going to calculate the mean of variable 1 for class A, and so this is going to be x1 bar A. I calculate the mean of variable 1 for class B, and that's x1 bar B, and I get x1 bar C, all right? And then I do the mean of the second column for class A, and that's going to be x2 bar A. I do the mean of the second column for class B observations, and I get x2 bar B. And then the mean of class C observations, column 2, and I get x2 bar C. Okay. The variance and standard deviation, you technically only have to do one or the other. I originally did the variances, and then I realized d-norm in R uses standard deviations. But I had already used my variances in other places, so I ended up having to go back and create standard deviations. I could have just taken the square root of the variances. But so basically, I'm just going to take column of x1, and I calculate the standard deviation. Okay, and this is what we have. Okay, so basically, you're just taking one column at a time, and you can calculate the standard deviation, or one column at a time, and you calculate the variance. Okay, and so you're going to have, in our case, we have 3 classes, and so I have 12. I effectively have 12 parameters to estimate. Okay, I've got the mean, 3 classes and 2 variables, right? x1 and x2, and so with x1 and x2 and 3 classes, and each normal distribution has 2 parameters to estimate, I have 12, right? And as you have more classes, you'd have more values to calculate. So so if I had 4 classes, then I would have 16 values to calculate, right? I would also need an x1 bar class D, x2 bar class D, standard deviation of variable 1 class D, and a standard deviation of variable 2 class D. So so is that okay? The fact that I have so many terms here, I don't technically need these variances. Okay, I could just get away with just calculating the standard deviations. Okay, but I'm doing them column wise. Okay, so I'm not taking the entire matrix. I'm just doing one column of the one column in our data at a time. Okay, and I have to do it for the observations that belong to A, the observations that belong to B, and the observations that belong to C. Is someone playing music? Okay. So that's so this is I get the means here, means and standard deviations, and then so now I plot the estimated contour lines with the naive assumption, okay? So with the naive assumption, this is what I'm estimating the contours to be, all right? So, so basically, we can see with the naive assumptions, the major and minor axes of each if each fit are parallel to the x1 and x2 axes, okay? And we can see, you know, for the red and the blue dots, it seems reasonable. For the green dots, it seems a little bit off, okay? So let me just kind of compare that to the estimated contour lines. So these are estimated from our data, okay? And then I'm overlaying, I don't know if you're able to see this, but the orange lines I've also plotted, and those are also estimated from the data, okay? And effectively, what's happening is I don't know if you guys can visualize this, okay? But look at one of these, like look at this orange ellipse, okay? So imagine you had like the selection tool. How do I do this? What slide is this? Slide 21. Okay, so imagine you have like a selection tool. And you had to draw a rectangle that will capture this, like the orange elliptical contour line, okay? And so you start in one corner, like right here, and you try to get a thing that captures the orange ellipse, right? So I'm trying to capture the biggest orange ellipse that goes around the green dots, okay? And then what ends up happening is rather than getting the with the naive assumption, we're basically fitting an ellipse that touches the edges of the rectangle, right? The rectangle has parallel and perpendicular values, okay? And we end up getting, for that rectangle, you know, I tried to cut my rectangle to touch the corners of the orange ellipse as closely as possible, and then now the purple ellipse matches that. Well, okay, anyway, basically we just look at the variance, the total variance that we see in x1 and x2, and then we just assume that there's no covariance between them. You don't, it's not a huge deal for the red and the blue dots, but for the green dots we can see this is quite different, right? And so for the green dots, when you recognize that there is covariance, we see that it's very unlikely to get an observation at 0, 0. Whereas when we assume that there's no covariance, okay, that x1 and x2 are independent, then suddenly it's not as unlikely to get an observation right here at 0, 0. Okay, so so I think I've summarized this. All right, so with the naive assumption, there's no covariance, so the major minor axes of the distribution ellipses are parallel to the plot axes. Okay, so here we're going to put a test case right here at 0, 0. And again, these are the distribution, estimated distributions under the naive assumption. Okay, so what is the probability that the observation belongs to class A, B, or C if our test case is 0, 0? Okay, so our calculations, again, this is kind of the same thing over and over again. Okay, the only thing really different, okay, everything else is pretty much the same. Posterior, prior, marginal, that's all the same. What changes is the way we calculate the likelihood. Okay, so this is, I highlighted this. All right, the likelihood will be calculated by using the product of independent normal density functions. So we're going to take, rather than using the multivariate normal, we're going to take the univariate normal and we're going to multiply them together. Okay, so the likelihood for class A of our observation 0, 0, okay, is first we're going to look at what's the probability of getting this 0 for the x1 variable, and what's the probability of getting this 0 for the x2 variable. So I say d norm, and then I'm going to do x new square bracket 1, the first value in that vector, okay? And this is d norm, so we give it mean is x1 bar a, standard deviation is SD1a. And then I just multiply that by d norm of x new 2, okay, the second value in our x new vector, using the mean is x2 bar a, and the standard deviation is standard deviation 2 underscore a, right? So maybe I'll just pause here, and I just want to make sure everybody's okay with getting these likelihood values as a product of two. This is using the regular old univariate normal density, d norm. So this is not the multivariate normal. It's d norm applied to the x1 variable multiplied by d norm times the x2 variable. And then the means and standard deviations of each of these things were estimated one at a time for each class using our training data, okay? So if that's good, go ahead and give me another green check mark, and let me give you the second answer to today's quiz. So today's quiz, the second answer is C as in cat. C as in cat for the second quiz. Okay. All right. About half of you have responded and said this is okay. I hope the other half of you are following along. I'm either getting yeses or nothing. So nope, not very many people say no. So I hope everything's okay. So so again, the key difference here is we estimated each of these things kind of independently, which is fine, and then we take the product of the two univariate normals. Okay. All right, and then so the priors and the marginals are found exactly the same way as before, so I'm not going to spend much time. And then the posterior, we do likelihood times prior divided by marginal. And so when we do this, okay, class B is still the most likely, around 84, 85%. But then class C is no longer the least likely, it's the second most likely, okay? Which, you know, might feel a little bit strange, or might feel a little off. But again, the naive assumption can be useful for us, especially if you have many x variables. Okay, and so one example from the book, and I didn't get into this, but is that if you can apply the naive Bayes classifier for doing text classification using a bag of words model. Okay, and so so this would be something like depending on just the words that appear in a sentence or document, you know, what classifying what the document is about. Okay, and so technically in that case, your x variables would be every single possible word that shows up, right? So you're going to have one of the x variables will be, you know, how many times did the word the appear? And then another x variable would be how many times did the word house appear? And then another x variable, x3, would be how many times did the word car appear? And x4 would be how many times did the word tree? And you'd have an x variable for every single word in your corpus or vocabulary, right? So if you encounter, let's say, 4,000 unique words in your different documents, you technically have 4,000 X variables, one for every single word. Um, and technically, in the English language, certain words are more likely to appear together than other words, right? So, like for example, if you have, you're more likely to see the word White House together than you are to see the words Blue House together, right? So, so technically, the words are not independent of each other, okay? And obviously, they're not independent of each other because, in the English language, there's certain structures that make sense and other structures don't, okay? But again, if you have 5,000 words in your vocabulary, then and in some cases, if you have a big document, you might have hundreds of thousands of words, in unique words again. Okay. So, but let's say you have 5,000 unique words in your corpus of documents, then you'd have a covariance term for every single variable in every single word, and you'd say like, what's the covariance between how many times the word house appears and how many times the word window appears, and what's the covariance between how many times the word house appears and how many times the word comet appears or something, right? And you'd have all of these things work, and so trying to estimate all of those covariances would be almost impossible, okay? And estimating all of those covariances would be impossible. And so it's easier to just say, you know what, the words are independent of each other. Okay, if the words are independent of each other, then we don't have to worry about the covariances. And then we can just say, what's the probability that this word appears, multiply it by the probability that this word appears, and we can just treat them as independent and just multiply them together, rather than trying to figure out the exact distribution and estimating the covariance of how many times one word should appear with another word. Okay. Okay, we have a question. Would white and white be unique? Capital white for like the White House versus lowercase white for just the color. I would not treat them as unique. I mean, you supposedly could, but I think that would just make things a little bit more complicated. And generally, we let everything be case insensitive. Otherwise, things get too wonky. Because if you ignore case, right? So generally, we would ignore case, and then there would be no way to tell the difference between white being used as a proper noun and white being used as a adjective. So if you had Snow White and Walter White as words in your thing, unfortunately for Snow White, her name is just two regular English words, and it would just be treated as English words. Certainly there's deficiencies in the bag of words model. Okay, just like there's deficiencies in the naive Bayes classifier. We know that things are not independent, and it might be not it might not be a good idea to assume that everything's independent. But again, trying to estimate all of the covariances between all of the variables could become impossible or highly ineffective to try to estimate the covariances between, how many times, pick two random words, right? Like probability and class. What's the covariance there? Well, they appear together in this document. How often does probability and class appear in other documents? And it's quite hard. So anyway, so in those cases, it's easier to just treat it as naive Bayes and the things being independent. Okay. we'll wrap up here, and that'll be it for today's lecture, covering kind of wrapping up the Bayes classifier and then giving this special case of the naive Bayes classifier. So we'll end there, and we'll see you guys on Friday.
Quick question, Professor.